We now turn to the details of evaluating area moments of inertia. Fundamentally, an area moment of inertia is evaluated as an area integral, which means it's a double spatial integral, which we would typically write as dA equals dx times dy. Multidimensional integration is typically a topic for a third semester calculus course, though, so we'll be reducing everything to a one-dimensional integral. This gets a little tricky because of the nonlinear nature of our integrand. If we are evaluating area moments as a double spatial integral, the differential element dA is just a point, and the tilde quantities x tilde and y tilde are no different than the spatial coordinates of the point. X tilde is equal to x and y tilde is equal to y. Now consider the 1D alternatives. If we're using a differential element consisting of a horizontal strip, as shown on the middle figure, there is no ambiguity in the definition of y tilde. Every material point comprising the strip has the same y coordinate, even though they all have different x coordinates. But in the definition of Ix, only y tilde appears in the integrand. Again, y tilde equals y, and we can evaluate Ix as the integral of y squared w of y dy. We run into difficulty, though, if we try to evaluate the area moment Ix as a 1D integral in x. Now every material point in the vertical strip has a different vertical position. When we were using this construction for a centroid calculation, it was okay, because the position appeared in the integrand as a linear function. We could compensate for every material point having a different vertical position because a material point just below the midpoint of the differential element, this one for instance, was exactly offset by a material point just above the midpoint by the same distance. But when the weighting of the position is nonlinear, in our case squared, this is not the case. The average of a squared position is not the same as the square of an average position. So we are not permitted to extend our practices for centroid calculations directly to those for area moment calculations. A complementary result occurs for calculation of Iy. We can use a vertical differential strip because every material point in that strip has the same x-coordinate, and x tilde is equal to x. It turns out there is a way to work around these restrictions, but to do that we need a concept from section 10.2. For now then, we'll restrict our 1D differential elements to horizontal strips for Ix and vertical strips for Iy. Let's now take a look at some examples. In example 1, we're asked to show that moments of inertia for a rectangle have certain functional forms. Our initial set of calculations will be for a centroidal coordinate system indicated by the primed axes in the figure. If we're calculating Ix prime, we need a horizontal strip that will have a thickness dy prime and an area increment will be the span b times dy prime. If we're evaluating Iy prime, we'll need a vertical strip that will have a thickness dx prime and our area increment dA prime will be the height times dx prime. For Ix prime, we're integrating our horizontal strip between the appropriate limits, which in this case go from minus h over 2 to plus h over 2. The y tilde is just the y coordinate, and dA prime is b dy prime. B is just a constant, so we can pull that out of the integrand, and then we're left with our integral over y prime, which will be 1/3 y prime cubed between the limits evaluated between the limits of minus h over 2 and plus h over 2. If we do that, we end up with an expression that the centroidal area moment of inertia about the x-axis, the x prime axis in this case, is b h cubed over 12. This is a fundamental result. It's going to be a building block for much of what we do later. By the same token, iy prime will be integrated over x prime, and the appropriate limits are from minus b over 2 to plus b over 2. The x tilde is just the position x prime, and the differential element is just the height times dx prime. So once again, we can pull the height h out of the integral, and we're left with the integral of x prime squared dx prime, which is 1/3 x prime cubed, evaluated between the limits of minus b over 2 and plus b over 2. And this ends up being hb cubed over 12. So we can see in comparing ix prime and iy prime that the roles of b and h have simply been transposed. The third quantity we're asked to evaluate is the polar moment of inertia about the centroid, and here is where the relationship between the polar moment and the area moments become quite useful. Our actual definition of the polar moment is this, and if we were going to evaluate that r tilde squared and integrate over the area for this rectangular cross-section, that might be quite difficult. But we know from the definitions of the polar moment and the two area moments that this is just equal to the sum of ix and iy. So we really don't need to evaluate anything here on the basis of an integral. We've got our values of ix prime and iy prime, and we can simply put those two things together. We have a common b times h that we can pull out in front, and then we have h squared plus b squared over 12. Finally, our last calculation is for ix. And here, this is going to look very much like our calculation for ix prime. The main difference is the limits of integration. In this case, we're integrating x from 0 to h. It's still the case that x tilde is going to correspond to the position y in this case instead of y prime, and our area increment we could write as b dy. So our area moment about the x-axis is going to be the integral from 0 to h now, not from minus h over 2 to plus h over 2, but from 0 to h, y squared b dy. And we'll see we're going to get the same result here that we had for ix prime. It's just that we're evaluating the result over different limits, and we end up with ix equals b h cubed over 3. In our second example, we're asked to find the polar moments of inertia, the j, c, or iz, for both a solid cylinder of radius 20 millimeters and an annular cylinder of inner radius 15 millimeters and outer radius 20 millimeters. Given the geometry of this problem, calculating ix and iy may be somewhat difficult, but calculating jc or j0 or iz is quite straightforward. So what we'll do here is position, we have our coordinate system here. And now think about the definition of j as this integral over the area of r tilde squared dA. Because of the circular symmetry of this, the most natural differential element for us to take is an annular element of differential thickness dr. In this case, every material point in that differential element is the same radial distance from the origin. So here, r tilde is just r, the radial position, and the differential area is the circumference of that annular element times its thickness, which is 2 pi r dr. And once again, we've turned an area integral into a one-dimensional integral. For the solid cylinder, the limits of integration will simply go from 0 to its outer radius. For the hollow cylinder, it would go from its inner radius to its outer radius, or we could think about subtracting a smaller radius solid cylinder from a larger radius solid cylinder. We pull the 2 pi out, we're left with an integral of r cubed dr, which is 1/4 r to the 4th between these limits. And we can see that for a solid cylinder, J is pi over 2 times the radius to the 4th. Again, this is an important building block that we'll come back to later. Now, one of the things to notice here is that because of the symmetry of this object, there's not going to be any different resistance to bending about the x-axis than it is about the y-axis. The circular object looks the same with respect to any orthogonal coordinate system that's positioned at its center. If we go back to our definition that J is equal to Ix plus Iy, and now from symmetry we understand that Ix is equal to Iy, then we have expressions for Ix and Iy without having to do any explicit integration. In fact, what we find is that Ix is equal to Iy is equal to J over 2, which is pi over 4 r to the 4th. From here, we can plug numbers in to get the actual numerical values involved in the problem. For r equals 20 millimeters for the solid cylinder, this number ends up being equal to 2.513 times 10 to the 5th millimeters to the 4th. And for the annular cylinder, or the hollow cylinder, again, we can think about this as the difference between a larger solid and a smaller solid. So this is just going to be 20 millimeters to the 4th minus 15 millimeters to the 4th. And that number turns out to be 1.718 times 10 to the 5th millimeters to the 4th. Finally, we end up with our third example where we have an area that's defined by these two bounding curves, and we want to find values of Ix and Iy. For Ix, we're again restricting ourselves to an area increment that's a horizontal strip, so this is going to be a width as a function of y dy. And for our calculation of Iy, we'll have a vertical strip, and this area increment will be a height that's a function of x dx. For calculation of Ix, we need the width, and here we have to rearrange our expressions a little bit. We've got y as a function of x, but we want to rearrange this as x as a function of y. And so we'll find that for our left bound, we just turn around y equals 1 plus x, so that this is x is y minus 1. And for our right bound, we subtract 1, multiply through by 5, and take the square root, so that this becomes the square root of 5 quantity y minus 1. Our width is the difference between those right and left bounds, or the square root of 5 times the quantity y minus 1 minus y minus 1. Our integral for Ix then is the integral from y equals 1 to y equals 6. Y tilde is just y, so we have y squared times the width of y, which ends up looking like this. This expression illustrates why our restriction to differential elements of certain orientations can be problematic. This particular integral can be evaluated, but we're going to need a substitution in order to be able to do it. We'll let u equal y minus 1, and we can see from that that an increment of u is just an increment of y. And that results in our expression for Ix becoming an integral from 0 to 5, now as y goes from 1 to 6, u plus 1 squared times the square root of 5u minus u du. We can multiply that out, and if we do, we get a difference between two integrals. The first one looks like square root 5 times the integral from 0 to 5 u to the 5 halves plus 2u to the 3 halves plus u to the 1 half du. And the second one is an integral from 0 to 5 u cubed plus 2u squared plus u du. Integrating, we get the following result. By comparison, our evaluation of Iy is relatively straightforward. We already have y as a function of x, and now we're integrating over x from 0 to 5 inches. X tilde is just x, so x tilde squared is x squared. And the height is just the difference between the top and bottom bounding curves, y as a function of x. So this becomes x squared times 1 plus x on top and 1 plus x squared over 5 on the bottom. And we end up with an integral from 0 to 5 of x squared times the quantity x minus x squared over 5 we have our first term is x cubed, and that integrates to 1/4 x to the 4th. The second term is x to the 4th over 5, and that integrates to 1/25 x to the 5th. Evaluated between these limits, we end up with a value of 31.25 inches to the 4th. What this illustration has shown us is that when we restrict ourselves to a differential element of a certain orientation, we can make the problem harder than it really needs to be. So when we transition to our next section, in section 10.2, we're we're going to look at a theorem which, among other things, is going to help remove this restriction on the orientation of our differential element.